Hello, everyone. It's a pleasure to be here, and thanks to the organizers for putting together such a nice event. Today, I would like to tell you a little bit about single-shot quantum error correction. So, in the first part of the talk, I will give you a very brief overview of quantum error correction. In particular, I will focus on topological codes, the decoding problem, and tell you how to handle the issue of imperfect measurements. And in the second part of the talk, I will focus on single-shot quantum error correction. And in particular, I will tell you how to realize single-shot quantum error correction with the 3D subsystem Tor code. This is a new topological code that we discovered last year. I will tell you how to realize single-shot decoding with this model. I will show to you some numerics, and then I will tell you a little bit how one can prove that this model indeed exhibits the property of single-shot quantum error correction. And I will summarize with a few remarks. So let's get started. The main topic of the conference is NISQ systems. However, NISQ devices is not all that we want. We actually want something more. We want to have scalable and reliable quantum computers. So a million, or maybe these days $1 billion question is, how do we construct quantum computers? And there are many researchers and companies that are actively working on this problem, and there are different paths that are being pursued. And the architectures that people consider are, for instance, trapped ions, superconducting circuits, photonic qubits. Different architectures provide different opportunities, but also come with different challenges. So, for instance, we may have better qubits, better quality of qubits, better quality of gates, better connectivity, but maybe the system is more difficult to scale up. But no matter what architecture we pick, realizing this reliable processing of quantum information is a very difficult task due to the nature of quantum information. It's very fragile. It can decohere very easily. So one can ask whether it is even possible. And from the theoretical perspective, we don't know any fundamental reasons why quantum computing cannot be realized. However, whether we can build a quantum computer is a different question, because we have to resolve many experimental and engineering problems. But from the theoretical perspective, we know how to build a scalable, reliable quantum computer, and two indispensable ideas that we need are quantum error correction and fault-tolerant methods. So let's talk more about those two. So here's how I view a path to fault tolerance that will allow us to have noisy components that we put together so that in a smart way, so that we can run some meaningful quantum algorithms. So first, we start with some physical system, and we understand the native operations in the system. For instance, we can have superconducting qubits, and then we can have entangling gates between nearest neighbor qubits. And then if the quality of our qubits and physical gates is sufficiently good, then using some clever quantum error correction techniques, we can realize a logical qubit and logical gates of much better quality. And at this point, we can abstract from the hardware. We can forget about the underlying physics, and we can treat our qubits and gates as ideal gates. And with those components, we can run our favorite quantum algorithm, for instance, Shor's factorization algorithm. And in the talk, I will be focusing on the middle part of this path. And here I would like to emphasize that the overhead due to quantum error correction is one of the major roadblocks to achieving fault tolerance. And we do need theoretical concepts to shave off those factors, to reduce the overhead due to quantum error correction. This is the area of active research. And in general, moving along this path is an enormous challenge, And this comes from the fact that there are very many components that can be optimized, but they have to be optimized in conjunction with other components. So first, we need to specify quantum error correcting codes that we use. So recently there has been a lot of effort, excitement to come up with good quantum LDPC codes. And then once we have some codes, we need to understand how to do error correction with those codes, what operators to measure, how to infer what corrections to apply from some classical data. For instance, yesterday we heard in Eugene's talk how to do error correction with LDPC codes. And lastly, we're not only after correcting errors, we actually want to implement some logical operations. And in the talk, I will not be talking about logical operations. I will focus on codes and correction strategies. So what is a code? A quantum code, very abstractly, is a subspace of the Hilbert space where we encode information. And typically, we assume that the Hilbert space admits a tensor product decomposition into smaller Hilbert spaces. Each of those small Hilbert spaces captures some finite dimensional system. And a typical assumption in quantum error correction and fault tolerance is that noise affects each of those constituents somewhat independently. So how do we tie this very abstract idea of a quantum code to reality? Here is where a notion of topological quantum codes come into play. It's an idea due to KITP, and here's how it goes. We take a surface of some manifold, for instance, a torus, and then we place qubits on the surface, and we can realize the code by measuring certain operators. And in case of topological codes, we require that the operators that we measure are geometrically local. So we only have access to this local region of the system. At the same time, the logical information is encoded non-locally in the system. So if we were to implement a logical operation, we would need to act on some non-local region, like for instance this non-contractible loop depicted here. I could say that we can view topological codes as a special case of quantum LDPC codes that come with this extra requirement that the parity checks are geometrically local. LDPC codes stand for low density parity check codes, which means that each qubit is affected only by is checked by a constant number of checks, and each check contains only a constant number of qubits. Topological codes turn out to be the leading candidates for quantum architectures because first we can realize them, for instance, in 2 dimensions. And they also provide very good protection from noise. And we also know how to implement fault-tolerant logical gates with them. And as a side remark, let me tell you that topological codes are not only interesting from the perspective of building a quantum computer, topological codes also provide insights into quantum many-body physics and illustrate a few concepts such as topological order. They provide a very concrete realization of exotic quantum phases of matter, or they can tell us a little bit about self-correction. But let's focus on quantum error correction. So how can we detect and correct errors? In this talk, I will focus on stabilizer and subsystem quantum error correcting codes. This is some class of error correcting codes that is relatively simple to analyze, yet quite powerful. So how do we proceed with detecting and correcting errors with stabilizer and subsystem codes? Well, we measure certain parity checks. Parity checks are just some Pauli operators. And from those measurements, we get some measurement outcomes, some bits of information. And this classical data is what we need and what we use to detect the presence of errors and find a corresponding recovery operator. For stabilizer and subsystem codes, the recovery operator would be some Pauli operator, and we can find it by implementing certain decoding algorithms that take as the input this classical data. So in this process of detecting and figuring out what to do, there are certain desirable features that we want to have. So first, as I already alluded to in a previous slide, our priority checks better be small, and also we need to know how to implement those priority checks with quantum circuits that are available in our hardware. For instance, with superconducting qubits, we can implement CNOT gates between nearest neighbors. And also, the other feature that we want to have is that the decoding algorithm that we use to process this classical information, they better be fast so that we can find corrections rather quickly. And we want our methods to infer what corrections to apply to exhibit good performance. We want to tolerate a high rate of noise. And ideally, we want our methods to be provable, meaning if we have a guarantee that there's just a few errors in the system, we want to know that we can correct them faithfully. So to make the discussion more concrete, let me show you an example. I'm sure many people in this room are very familiar with the 2D Toric code and how to do error correction with it. So the 2D Toric code can be defined on the square lattice by placing qubits on the edges of the square lattice. And by measuring priority checks, there is the Pauli-Z plaquette operator that we measure and Pauli-X vertex operator that we measure. And we use Z plaquettes to correct X errors, X vertex operators to correct Z errors. So let's, without lots of generality, let's think of just correcting Z errors. So I will measure X priority checks, and some of them will give me -1 outcomes. I depicted them as red dots, and those red dots is the syndrome that I observe. Those points are also the endpoints of string-like Z errors that happen in the system. I don't know what string-like Z errors happen in the system, but what I do know is their endpoints. So now the decoding problem can be viewed as I have some collection of points and I need to pair them up. I need to find a way how to pair them up, and this will tell me what Pauli correction I need to implement. And the decoding would be successful if the errors combined with the correction are equivalent up to some stabilizer operator. And this problem admits an efficient solution, for instance, with the minimum wave perfect matching decoder. What it is, it's like basically I construct some fully connected graph, and I find a matching in this graph of the smallest total weight. And this allows me to find the most likely error. So notice that here, in solving this problem, I rely on this crucial fact that there is some global Z2 symmetry, namely the number of points that I need to pair up is even. But could something go wrong with it? Well, so far I was telling you about perfect measurements, and some measurements outcomes may be wrong. So for instance, I might misinterpret that measurement outcome, and now if I have odd number of points, I won't be able to pair them up anymore. So what do we do? Well, there's a standard solution to this problem. Namely, we just need to repeat measurements in order to gain confidence in the measurement outcomes. So we can do that with the 2D Toric code, but then repeating measurements, collecting the data takes some time. And now the structure that we have to analyze is 2 plus 1D. There is some space-time structure. So this is not good. There is the slowdown that we suffer from, namely on that the logical clock speed is reduced compared to the physical clock speed. Also, as I just said, the decoding problem becomes more complex because we need to store and process not only one shot of measurement outcomes, but the history of measurement outcomes, and we need to process it jointly. And also, we need to worry about like time-correlated errors or errors that happen during those repeated rounds of measurements. The problem gets just messy. So how can we go about it? Well, recently there have been quite a few works telling us how one can avoid repeating measurements. But if those results are applied to the 2D toric code, then we will have to sacrifice the geometric locality of the toric code and constant weight of the parity checks that we measure. And this is not something that we want to sacrifice. So is there a different way out? Well, there's this beautiful idea of single-shot quantum error correction due to bond-beam. What it is, it's about the possibility to implement robust quantum error correction with only one round of imperfect measurements of geometrical local parity checks. So I would like to stress out that, we don't have to repeat measurements. Our measurements can be noisy, and we don't have to measure non-local big weight parity checks. So can we apply this idea to the toric code to gain the robustness against measurement errors? So this brings me to the second part of my talk, where I would like to tell you how to realize single-shot quantum error correction with the toric code in 3 spatial dimensions. And what is this? The 3D subsystem toric code is a version of the toric code. It's a subsystem version of the toric code, and it can be realized on the cubic lattice. So here I depicted some region of the cubic lattice. Notice that the volumes of the cubic lattice can be colored in red and blue in a checkerboard fashion. And I will define the code first by placing qubits on the edges of the lattice. And then in the bulk, I will be measuring parity checks of Z and X type. And namely, for every blue cube, I will be measuring 8 weight 3 Z type parity checks. And for every red cube, I will be measuring 8 weight 3 X type checks, as depicted here. So this is what the bulk of the model looks like. Along the boundary, we have to make some adjustments and measure the operators that I depicted here. But this is not essential. One need to make some adjustments. And then, if you're paying some attention here, you may notice that some operators, parity check operators that we measure, don't commute. For instance, the blue Z triangle here and the red X triangle there, they overlap on 1 qubit, thus they don't commute. But is that a bug? Well, it's not a bug, it's a feature. It's a subsystem code. It's not a stabilizer code, it's a subsystem code. It's a slight generalization of stabilizer code. So we measure those parity check operators. And from those parity check operators, we can figure out the measurement outcomes of stabilizer operators. So stabilizer operators are the operators that commute with every parity check. And in this model, we can form stabilizer operators by taking parity checks around each cube. So this is a stabilizer operator in the model. For every cube, we will have parity check of Z type for every blue cube, and for every red cube, we will have parity check of X type. And notice that we can form this weight 12 operator by multiplying a quadruple of parity checks like that, or a different quadruple. So there's 2 ways to realize a stabilizer operator. Either I take one set of parity checks or the other set of parity checks. And stabilizer operators are the ones that tell us, that detect the errors, tell us about the presence of the errors in the system. So what's the decoding problem for the subsystem toric code? So it turns out that it is very similar to the 2D toric code, a decoding problem. Namely, we will have some string-like errors, and we will detect them by observing certain point-like syndromes, their endpoints. So it's analogous to the 2D Tor code. It's just that the space that we operate within is three-dimensional. So this is what we see. We don't see the positions of string-like errors. We just see their endpoints. Okay, so that's it. But there's a twist to the problem. So we measure more than just stabilizer operators. I told you that we measure parity checks, and then from those parity checks, we can infer what the measurement outcomes of the stabilizers operators would be if we measure those stabilizer operators. And remember, I was telling you that the stabilizer operator can be formed in one way or the other way. So let me color those two sets of parity checks in yellow and green. So notice that the parity checks that I measure are somewhat redundant. And namely, if I multiply all of them around each cube, I will get the identity operator. So what it means is that the measurement outcomes of those parity checks, if I were to multiply them, I would be guaranteed to get a +1. So this redundancy gives rise to some local symmetry, some local Z2 symmetry. So what I can say in different words is that parity check outcomes satisfy certain local meta checks. And because of that, I can visualize their outcomes as some loop-like objects that I refer to as the flux. So the flux will be all the parity checks that return -1 outcome. So those guys will form closed loops. They will fluctuate very much within the system, and nevertheless they will stay closed loops. And interestingly, I will have two colors of this flux. So there would be a yellow flux that corresponds to -1 parity checks of the first kind, and a green flux that corresponds to -1 parity checks of the second kind. And the locations where the flux changes color from yellow to green is basically the locations of point-like syndromes. So the picture that you should have in mind is that you measure this flux, it's all over the system, but it satisfies the local Z2 symmetry. It has to form closed loops, and I can look at it and find the positions where one color turns into the other color, and this is the locations of point-like syndromes. And this is crucial. However, on this slide, I haven't told you about measurement errors. This is just perfect measurement outcomes. But this is not the reality. In reality, we will have some measurement outcomes, and what we will see is some configuration of the flux, noisy flux, which does not form closed loops. So is that a problem? Well, it's not a problem. And here's how we solve it. So an approach to single-shot decoding consists of the 3 steps. In the first step, we'll repair the loop-like structure of the syndrome by closing up those broken loops. And once we have a collection of closed loops, well, they can terminate at the boundary, but don't pay attention to the boundary. If you have a collection of closed loops, then you can estimate reliably the positions where the green flux turns into the yellow flux. This tells you about the point-like syndrome. And then in the third step, you will use this point-like syndrome to find error correction in the same way as you would do in the 2D Tor code. Interestingly, both steps 1 and 3 can be realized efficiently can be solved efficiently with the minimum wave perfect matching algorithm. And if we choose minimum wave perfect matching algorithm, we will get good performance. It's efficient, but it's also needed in our analytic proof. So this is the sketch how single-shot decoding works. And now let me show to you, let me convince you that it actually works. What we've done is we ran some numerics. We looked at the IID Pauli X noise with some rate P, And also there was the measurement noise that flips the measurement outcome with probability P. And what we can study is how errors accumulate during repeated T rounds of quantum error correction with single-shot decoder. So in one round of error correction, what I do is I add new errors to the pre-existing residual noise. Then I measure parity checks. The measurements can be wrong. Then I use single-shot minimum wave perfect matching decoder that I described in the previous slide that uses only the information that I extracted in that round of error correction. And then I repeat. And so what I depict here in this figure is the logical failure rate as a function of the physical error rate for different code distances. And this is after 4 consecutive rounds of quantum error correction. And what we can read off from this plot is that there would be some threshold at around 1.05 or something like that. Okay, so now what we can look at is how this plot would change if we consider more rounds of quantum error correction, if we increase the t, the parameter t here. So this is what we can call as the storage threshold. Basically, we're interested in the limiting behavior of the threshold. So this point in this plot is basically read off from the plot that we just discussed. So, and we see that the storage threshold of the subsystem toric code is above 1%. And for the experts in the audience, this value constitutes around 3.5 improvement over the threshold of the 3D gauge color code. That was basically the first model that demonstrated single-shot quantum error correction. But here, I would like to emphasize that this improvement will only increase if we consider the circuit noise, because with the subsystem toric code, the parity checks that we measure are only of weight 3, and with the gauge color code, we have to measure parity checks of weight 4 and 6. Okay, so I hope this gives you some confidence that a single-shot error correction works here, but can we actually prove it? So before I tell you what we prove, let me remind you that what single-shot decoding does, it suppresses the errors. We are unable to remove them altogether because our measurement outcomes are not perfect, so we may be always fooled a little bit. But the point is that the residual noise that is left in the system will be kept under control. And this is exactly what we can prove. To prove that a system has the single-shot quantum error correction property is to prove that the residual noise that is kept in the system is kept under control. And this intuition can be formalized with the following theorem. For sufficiently small parameters eta and tau that capture the measurement error rate and the physical error rate, there exists some other 2 parameters, tau prime and delta, such that the following inclusion is satisfied. So let me slowly walk you through this inclusion. So here are the nodes, a class of channels that describe single-shot minimum wave perfect matching decoding that we discussed over the past few slides. This parameter eta captures the measurement error rate. Okay, so that's R. N is a class of channels that captures local stochastic noise. And this local stochastic noise is described by 2 parameters, tau and epsilon. Tau captures, you should think of tau as the physical error rate, and epsilon is the logical error rate if we applied ideal single-shot minimum wave perfect matching decoder to that noise. So tau is the physical error rate, epsilon is the logical error rate, and pi is just the code projector. So this theorem says that if we have some state encoded in the subsystem toric code, and the noise acts on it, and then we do some recovery. We implement the single-shot decoding. Then what is left is basically the state that is in the subsystem toric code, and there's some residual noise affecting it, and the parameters of the residual noise change somewhat. So the non-trivial part of the theorem is basically how those parameters of the residual noise behave as a function of tau, epsilon, eta. The the error rate of the residual noise, tau prime, is suppressed if the measurement error rate, eta, is suppressed. Basically, in the limit of eta going to 0, in the limit of perfect measurement, we would be able to eradicate the residual noise. It's gonna be gone. That's the first part. And the second part is that the increase in the logical error rate, this delta parameter here, vanishes if we just keep growing our system. So in the limit of infinite system, the increment in the logical error rate would be basically 0. So with this theorem, we can ask what happens if we implement t subsequent rounds of single-shot error correction, and we get some inclusion as well. And what is interesting to know is that the residual noise stays tau bounded, no matter how long for a very long time. It is kept under control. And a non-trivial statement is that the logical error rate grows only linearly in t. Because at each point, there is some chance that the noise implements the logical error, but our decoding suppresses the residual noise. It does not accumulate in any way that is not benign. It just accumulates in this slow fashion, in a linearly with the number of rounds of quantum error correction that we implement.
Question. Can you clarify the definition of epsilon again? Because if you are below the threshold, the logical failure rate should go to 0 for infinite system size, right?
Yes. So those quantities are defined for some finite size system, and basically epsilon would scale. If you're below the threshold, it would be exponentially suppressed in L, but it would not be 0. So yeah, it's basically this epsilon is some sort of like a function of L.
Okay, thanks.
Mm-hmm. Okay, so since I don't have much time, it's good that I start talking about, I will still tell you a few remarks and summarize the talk. So at this point, you still may wonder, I've been telling you that this is the subsystem toric code, but what does this model have to do with the 3D stabilizer toric code that you may be familiar with? Well, those two models are related by code switching. So what I mean by that is if I have the code word in the 3D subsystem toric code, I can transfer it into a code word of the 3D stabilizer toric code by gauge fixing, by fixing the state of the gauge qubits that I have in the 3D subsystem toric code. And vice versa, if I have a code word in the 3D stabilizer toric code, it is trivially a code word of the 3D subsystem toric code for which gauge qubits are put in some special state. So another remark that I would like to make is that this model is the first genuine subsystem version of the toric code. And this is quite interesting because there's this intimate connection between the toric and color codes, between subsystem toric code and subsystem color code. Namely, they are equivalent. The color codes are multiple copies of the toric code. And we knew that there exists a subsystem version of the color code, known the gauge color code, that was invented back in 2013. But our version is basically the first subsystem version of the toric code, which was bound to exist because of this kind of analogy. So That's kind of neat. Also, another thing that I would like to mention to you is that I discussed with you the subsystem toric code in 3 dimensions with qubits, but we can define it in 3 or higher dimensions. And also, we don't have to work with Z2, we can work with any finite abelian group. One extra remark that I would like to highlight is we can do logical operations with this code. I don't have time to explain to you how it can be done, but based on the 3D subsystem toric code, we can realize fault-tolerant universal computation. And in particular, in this scheme, we can have transversal logical T gate, Hadamard, and CNOT. Notice that there is no contradiction with Isting-Kneel theorem. If you're confused, ask me about it. Importantly, in this approach, we can realize each logical gate in constant time overhead. So this allows you to do a very quick, reliable computation. Okay, so this brings me to the summary of my talk. In the talk, we were talking about single-shot quantum error correction. This is a different approach to solving the problem of imperfect measurements and how to do robust error correction in such a case. So the take-home message is that if you have imperfect measurements, you don't have to repeat them. You can just use single-shot error correction. You measure your operators once, and then you're good to go. And you can realize this idea with the 3D subsystem toric code. And here, I'd like to emphasize that what we measure is geometrically local parity checks. So the 3D subsystem toric code that I try to illustrate to you is a new beast in the zoo of quantum error correcting codes. And to me, it's the most transparent illustration of single-shot quantum error correction. We measure the parity checks, they form flags, and then from the flags we can infer point-like syndromes, and then using those point-like syndromes we can do reliable error correction. To me, this is the most transparent illustration of single-shot error correction. And on top of that, this model exhibits a good performance that is on a par with, say, the performance of the 2D toric code. Of course, there is a caveat that I'm using here 3 spatial dimensions, but, well, nothing is, there's no free lunch. There are a couple of future directions that are interesting to look at. So first, we may ask, how realistic is this approach to really realize fault-tolerant universal computation? And then we would need to do some detailed resource analysis, thinking about layouts, circuit schedules, and so on and so forth. And also with this phenomenon of single-shot quantum error correction, it would be interesting to pinpoint and understand better the connection to self-correction. And another very open-ended question is, does single-shot quantum error correction lead to new physics that we may be interested in exploring? And with that, I would like to thank for your attention.
Thanks, Alex. Do you think you can say anything about self-correction using this model?
Not really, not really. But like single-shot error correction is a way to realize. It's like self-correction, but you need to do something. So yeah, but yeah, it would be interesting to understand the connection.
Yeah, thanks for the talk. So I had a question related to the new physics, right? You had your last slide. So I wonder, can we reinterpret your results about the one single-shot QEC as saying something about finite temperature stability of certain phases? So the usual 3D stabilizer toric code, we know it's not stable as a quantum phase, any finite temperature. Is your modified, if you interpret your the measurements as a defining Hamiltonian, do you think there's some finite temperature quantum phase there?
So yeah, that's basically the direction that I would like to think of. The way I think about this single-shot error correction, measuring the parity checked and inferring the stabilizer operators, doing some corrections, is maybe some way to engineer one-form symmetries in the system. So that's how I would view this model, for instance, that this is a way to engineer one-form symmetries in the system.
Thanks for the talk. So is there some more general principle that you can abstract out of your model of what features the code would need to have in order to have this one-shot error correction?
The underlying feature that we need is this redundancy among our parity checks. With this model, we have this feature that parity check measurement outcomes form closed loops, and such a feature should be leveraged. I don't have like a full story to answer to your question, but my gut feeling tells me that this is the important feature.
Thanks.
Yeah, single shot quantum error correcting impossible in 2D?
So yes, if you think about stabilizer codes, if you think about subsystem codes, we don't know. But it's unlikely. It's unlikely.
Is there any other question?
I was just wondering if you could say a little bit more about how the transversal universal gate set doesn't conflict.
Yeah. So thanks for this question, because this allows me to clarify this item that I didn't have a chance to talk about. The way you avoid Easton-Kneel no-go theorem is that you change the code. Basically, you will have the Hadamard gate in the subsystem code, but you will have the T-gate in the stabilizer code. So in order to implement the T-gate, you would need to gauge fix your code, then do the T-gate. And this process of gauge fixing is what circumvents the Easton-Kneel.
Could I just follow up Thibault's question and ask about this single shot in, say, 3D? So in like some expander codes, there's like single shot properties without having these relations, is that right? And is there any possibility for that in 3D, or do you think it has to be the relations to have single shot?
So yes, so if you have some hyperbolic space, if you have some expanding some expander code, you can get some single shot error correction property. But if you are thinking about Euclidean spaces, as I was in this talk, I would say that you need those local relations.
Are there any like results along those lines?
Yes, so this is basically more in the setting of, single shot error correction that I talked about is in this context of stochastic noise, local stochastic noise, but you can think about single shot error correction in the adversarial noise. This is what Earl Campbell looked at, and you would need to basically think of what he was doing, yes. But there are certain properties, for instance, the soundness and so on and so forth, that tell you whether single shot error correction is possible.
Thanks.
I have one related question to the gates. You said you can do transversal T-gate when you go to the stabilizer code. So conventionally, we would do a transversal T-gate in the color code and do a CCZ gate in the toric code. So do you do a mapping to a color code? Or?
So the code that you need to use is not the one that I showed you on this cuboid region. You need to consider some tetrahedral region. And the transversal gate is gonna be implemented on the physical level with T gates at certain qubits and CCZ gates at certain triples of qubits. But it's gonna be transversal, meaning it's gonna be implemented as a tensor product of local unitaries.
Thank you.
Yeah, I just wanted to follow up on Matthew's question. So, I mean, have you studied at all, like, how many layers you need in 3 dimensions? How does it have to be linear to get the threshold, or?
Oh yeah, that's an interesting question. So if you have some bias in your noise, the cuboidal region that you want to consider, its linear dimensions would be proportional to log probabilities of your X error, Z error, and measurement error. So you don't have to consider L by L by L region. It can be a thin slab.
Okay, if there are no further questions, let's thank Alex again for the